In this topic, we will solve the kinetics problem in terms of cylindrical coordinate system. Uh, in cylindrical coordinate, okay, it is same as the normal and tangential coordinate that we already know exactly the path. However, the path is maybe more complex, or the problem may have other attributes that make it desirable to use cylindrical coordinate system instead. So equilibrium equation in cylindrical coordinate system that we use theta and c coordinates may be expressed in scalar form like this. That is decomposed into three scalar equation, that is summation f equal to mar, while mar is equal to r double dot minus r dot theta squared, and summation f theta equal to ma theta, where m theta is composed of r theta dot dot minus 2r dot theta dot. And the last one is summation fc equal to mc double dot. Okay, so if particle is constrained to move in plane, that is in r and theta only, so then it means that the c coordinate is constant. So the only first two equations, that is in polar coordinate, in plane, we use necessarily these two equations. The coordinate system in this case is become polar coordinate system. Okay, as we consider just only this. And we will consider the normal and tangential and normal force that is acting along the path. Okay, so if force P cause the particle to move along the path defined by R equal to F theta, like this, we know the path in polar coordinate. The normal force N exerted by the path on the particle is always perpendicular to the path. Is it perpendicular to the path? It is maybe not at the same directions of R. Okay, so if we consider this particle, okay, R is in this direction. This is R direction. Okay, but normal is maybe not collide with the R. Okay, it's perpendicular to R, to the path. Okay, this is the path for this case. Okay, the path is along the tangent line. Okay, so it's perpendicular to the path, to the tangent. Sorry, it's perpendicular to the tangent. And the friction force F is always acts along the tangent in the opposite directions of motion. The directions of normal and friction force can be specified relative to the radial coordinate by using angle sign. Angle sign like this. The angle sign. We have the radial direction over here, and we have the tangent direction over here. This is tangent direction. Okay. So in order to determine the angle sign, okay, let's take a look this picture. Okay, so for this case, if we have the fixed reference point over here, and the path is defined by the blue line. Okay, for the position for this position, and the particles is moving with the finite angle d theta. Okay, so then we have the small distance r d theta over here, and with the increment of the r over here. So then if we take a look this angle, this rectangle, we have this triangle, that is this length is d theta, and this dr. Okay, and this distance, okay, this distance among this is the tangential direction. Okay, and we may consider this as the angle sine. The angle sine that measure from the radial direction. This is the radial direction to tangent. Okay, that is we see that this is the angle sine. Okay, so from this triangle, we find that tan sine is equal to d theta by dr. So it means that tan sine is equal to r divided by dr by d theta. That is, we have this relationship to determine the angle between tangent and r direction. That is, we can use this angle to find the normal direction also. So let's take a look at this example. The ball P is guided along the vertical circular path. And the weight of the ball is 0.5 pounds. And we know that the arm OA is moving with the angular velocity of theta dot of 0.4 radian per second and angular acceleration of 0.8 radian per second square with RC. RC is over here. This is the radius of circular path, which is equal to 0.4 foot. But R is measured from the fixed point O to the particle P over here. Okay, we would like to determine the force of arm OA on the ball when theta equal to 30 degrees. Okay, so we starting with draw the free body diagram, and we know that the acceleration in r and in theta direction is composed of this term is composed is derived from theta dot that's already given from the problem, and we also have to know r dot and r dot dot also. According to this, we know that the function r, that is the position of particle p in polar coordinate, is defined by r equal to r 2rc cosine theta. This is rc and it is circular path. So then if this rc, so then this is rc also. So then what does it mean? This is angle theta, right? So then this is equal to rc cosine theta. And then because we have two radius, so then this is rc cosine theta also. So then it's become r is become 2rc cosine theta. According to this, we can take the first derivative to this equation to get r dot. That is become 2rc. Take derivative to cosine, it's become minus sine theta and theta dot. That is, we have r dot. It's become like this. And after we take the second derivative to this equation, that is, we take the first derivative to r dot, we will have the combination of these two terms. That is, we may keep 2rc's become constant, and we have this term theta dot and sine theta. Okay, so then we take the first derivative of sine theta, we become cosine theta and theta dot. So then we have the term of theta dot square over here. And after that, we keep sine theta to be constant. We take the last term, the last term, that is theta dot, is become theta double dot over here. And then we get the derivation of double dot like this. Okay. From this value, we consider the free body diagram and kinetic diagram. According to this picture, this is the r axis. Okay, and This is theta axis. Okay. So when we consider the free body diagram of the ball, is composed of the weight mg that's go downward. Okay. And the normal force acting on the ball is composed of two normal force. First one is the normal force Ns that is perpendicular to the path line. This is the tangential direction. Okay, and this is the normal direction at this point. Okay, so the normal force, the first normal force is perpendicular to the tangent. Okay, that is become Ns. And another one, this is the normal force perpendicular to the arm OA, to push the ball direct to the path. Okay, that is NOA. So now we have two force that is composed of two normal force that is composed of NS and NOA. Okay, acting along the path like this. Okay. So from this, we may find that NS, this is the direction of NS. That is when we see that the angle between NS and R is equal to theta. Okay, but angle, according to this, we can derive the equation of motion. We can derive the equation of motion at the theta equal to 30 degree. We found that R dot and R double dot is become like this. This is for kinematics. And after that, we can determine the acceleration components in R and in theta from the formula that we already know. Substitute each value, we get the acceleration AR and A theta like this. And then from the equation of motion, when we consider summation of force in R direction equal to MAR, we decompose the force, that is this is R direction. Okay, this is NS. Okay, this is angle theta. So then this is theta. Okay, so after we decompose the NS to R direction, okay, this is a positive direction of R. We have NS cosine theta. NS cosine theta. Now theta is equal to 30 degrees. Okay, in the vertical axis and the theta axis is equal to theta also. From this picture, we can see that the equation of motion in R direction is equal to NS cosine 30 degrees. And this is the weight, that is 0.5 sine 30 degrees. And it's equal to M. That is, we know that the weight is in pound. Okay, the weight is 0.5 pounds. So then we have to determine for mass, we have to divide it by G. Okay, G is equal to 32.2 foot per second square. Okay, and time AR we already determined. AR is equal to minus 0.542 foot per second square. Okay, that is you will see that AR actually it is negative because it is opposite to the positive direction. Okay, as we know that it is a gold circular path, so then it should be the direction is toward the acceleration is maybe toward to the center of curvature, right? And now it's AR that is toward it may be like in this direction, AR, it should be in this direction. This is opposite to the positive R. Okay, so from this equation, we can determine for NS, that is the normal force, the first normal force, NS can be determined and is equal to 0.279 pounds. Okay, so let's take a look for equation of motion in theta direction. For theta direction, we do the same thing. That is, we have this angle, that is, this angle is theta. So then this is our direction, and this is theta, right? And this is theta direction, and this is theta also. When we decompose the force into the theta direction, NOA is already in theta direction, and it is in positive theta. That is, this is the positive one. So then NOA is the positive, and it is equal to NS sine 30 degree. NS, we already know NS is equal to, this is NS, NS is equal to 0.279 pounds. So then we have this component that is NS sine 30 degree and minus the weight that is 0.5 cosine 30 degree, which is opposite to theta, to positive theta direction, and it's equal to mass times a theta that we already derived. This is equal to 0.426. After that, we can solve for NOA that is equal to 0.3 pounds. That's complete this problem.